Hello, welcome. This presentation is on operational challenges of solar PV plus storage power plants and modeling recommendations. This presentation is based on an open access paper published in IEEE Power and Energy Society's Open Access Journal. And this paper is the result of collaboration between University of South Florida and the Electrical Power Research Institute. So here we are talking about a hybrid power plant. It usually consists of solar PVs from one vendor and then battery energy system storage BESS from another vendor. So two vendors usually will design different inverters, but there will be a power plant level control center. And all these inverters from solar PV and BESS, they will accept the commands from the same plant level control. So that will pose some operational challenges when you have parallel inverters as well as you have plant level control. So today's main topic is on the plant level control delay. What's the influence on the plant level control delay? We will talk about the three types of operational challenges like watt-to-watt oscillations and frequency control caused oscillations and overvoltage. Then another topic will be about how do we model delay in analytical modeling framework like a small signal analytic toolbox that can give you eigenvalue, this type of thing. But first of all, in fact, there are lots of operational challenges. So in the paper has covered total eight operational challenges. So today's talk will focus on challenge 1 and 2. And for the rest of challenges, they have been documented in the appendix. Some of them have also been covered in the previous presentation to NERC, like the PLL large angle deviation upon grid voltage drop. And this one sort of like trying to explain the Texas Odessa event. There will be a grid fault, voltage dip to 70%, and remote solar PV 200 miles away from the fault will see a large angle deviation. So what that's in fact it's a very interesting characteristic of grid follow inverter when they use PLL frame. Challenge 4 is about two inverter interaction. Whenever you have parallel inverters, if they are not designed very well, probably common mode or circulating oscillations can be seen. Solar PV ramp down, ramp up, ramp down issue could be delay caused, but there can also be some other reasons. However, there was one that have been talked about, that is delay caused one. So then the last two will be shunt and series compensation related issues, because those capacitors, they will introduce the LC mode in the electrical side. Then in the solar PV side or the inverter IBR side, there will be other control modes. For example, phase locked loop, they may interact with each other and cause some issues. So these are the total 8 operating challenges that we have summarized. So today we are going to use a testbed and some simple analysis, then use a testbed for demonstration. So this is the testbed that we are going to use. It's a 100 megawatt power plant, including 50 megawatt solar PV and 50 megawatt BESS. And then solar PV is connected to the point of interconnection, POI, through 10 kilometer cable. On the other hand, BESS is directly connected to POI through just a transformer. In the plant level, it's the power plant controller will measure, will get all the measurements from just the POI bus, then shown just after transformer, big transformer. The inverter control, then you will look at two inverter type. You control the PV bus, the solar PV bus, and the BESS bus. These are the measurements that for solar PV. And all the parameter has been given in the paper. The grid strength, we think the grid strength is about 0.3, 0.2, this kind of level. So SCI equals 5 or 6, 5 or 4. So let's look at the control. we'll look at the controls. So the main thing that we are going to pay attention is the plant level control. So inverter level control is the same PQ grid following type of control. It consists like in the current control very fast, then outer to regulate P and Q. And the PLL is used to generate the angle synchronized with the grid. Both of them are solar PV and BESS. They are using very same PQ level control. But plant level, if we take a quick look at plant level control, so the P command and Q command from to the inverter are all generated by plant level control. Now, plant level control use the measurement of voltage to generate the reactive power. However, there's a delay. We have to put there to send the command to the inverter. And then for the frequency control, usually people will use either measure frequency to do Joule control to send the power command, like a pop, real pop command to the inverter. Or sometimes you can see that actually people use they'll use not only just Joule control, but in addition of Joule, there's an additional feedback control of the real power. So these are the plant level control. So for now, let's just take a look of how these delay will influence the entire system. And usually solar PV delay and the BESS delay, they will be different values. One is called T1 and the other one is T2. And their values could be like, for example, 50 microseconds or 100 microseconds, this kind of level. So to like 200 microseconds, 300 like millisecond level. So let's look at the first issue. The first issue that we're going to talk about is called voltage var oscillations. So voltage var oscillation can be using a very simple feedback system to explain this. So for example, we have the POI, that's measurement of the voltage, the feedback control that there's a PI controller generated the reactive power command. So here we just think about aggregated influence, not too much on the inverter level stuff. So, so this after the delay, then the reactive power command was sent to the inverter, and the inverter will send generated reactive power and through sort of like low pass filter, 1 divided by 1 plus TS low pass filter to consider its delay. Consider it's like a control. But then this injected reactive power, of course, will influence the POI voltage. And the influence is related to the grid strength. If the grid impedance XG is large, or grid strength, the grid is weak, or XG is large, then that's the impedance, equivalent impedance. Then this is XG, right? So that's a relationship. So therefore, it's a very simple feedback loop that we can think about. And for this feedback loop, you can plot the loop gain, the entire loop gain. It's just like a PI controller delay and this influence. And here that you can take a quick look at two delay. One is at 150 milliseconds, the blue and the red line. Then the blue line is 200 milliseconds. So what happens is that you can see that the phase will shift from -80 to positive 180 at 1 Hertz, and the other one will be shifting at 2 Hertz. So it can easily see that, for the same thing, that the delay can influence the shifting frequency, but shifting frequency will influence, the shifting frequency actually determine the oscillation, in future determine the oscillation. Now the next thing that we're looking at is the loop gain magnitude. If the gain is large, of course, then the system will be pushed above 0 dB at the shifting frequency, then the system will suffer oscillations. Otherwise, system is stable. So the gain of the voltage controller will be influence the stability. So of course, then larger gain, weaker grid strength, XG, and all this larger, then you can see oscillations. And then the delay, basically, of course, delay is sort of like you have large delay, then you move the oscillation frequency to smaller. But smaller is bad because the gain is usually larger in the low frequency region. So that's the oscillation voltage var voltage feedback system. So the simplified model did not consider the real power effect, but in fact, the blue box, there's a we can add the blue box to show the real power impact. So the real power impact is basically the grid is weak and the real power is exporting is higher. Then this blue box will be greater than 1. It's greater than 1 in the low frequency region. It basically says the voltage is become more sensitive to the reactive power. Okay, so, and of course, then you ramp up a power, you probably just see the effect that the oscillation can increase, can be generated just by ramping up power. That's what happens in the other cases, in this SC case. Okay, so this one is explain that yes, you expect to see the what will happen, the oscillations that if the delay is large, if there's delay, then the grid become weaker, then we expect to see some issues. So in the next slide, just showing that what if you have, instead of PI controller, just a P control, what will happen? Yeah, P control, the blue line is P control, red line is PI controller. Yeah, P controller is slightly better as long as you can interpret this body diagram. So I'm not going to talk about it one by one. Just look at demo. So here's a demo. This demo is still, we are using PI controller, right? So the left side is just looking at the system that, yes, so although we are doing line tripping, but the grid is not that super weak. It's just ICCF becomes 3, become 5, so it's not that big. But however, you can see this grid, the voltage controller has a pretty large gain, 3 plus 30S, compared to the next one is 2 plus 20S. So therefore, the oscillation will show up in the, especially in the voltage and Q, right? Voltage and Q will show up, and V and Q is generally, you can see that are in phase. Like what V and Q is in phase. And then if you ramp down power, you can see slightly it becomes better. Right? Ramp down power by half, slightly better. All right. So that's the basically because of the larger gain. The next thing is looking at the grid is, gain is not super large, but the system becomes weak as well. So both cases here, the system becomes weak. And then we can see again that the voltage oscillation come up and Q up and P is also up, the oscillations, so voltage and real power. So this one is like the grid becomes even weaker than you can also see more oscillations in the real power, right, compared to the left side. So both cases are sort of like due to the large gain, due to the voltage control delay. And this is 150 milliseconds, so we see 2 Hertz oscillations. Okay, so now that's the voltage. You can classify this type as volt-var oscillations, right? So it's generally, we can just say this is a volt-var oscillations. All right, so next we are looking at the second type of the plant level control, the frequency control. So we have plant level, have voltage control. Now we're also looking at the frequency control. So first we consider droop, right? So this is the plant level droop control, have power frequency measurement, generate the power order, and after delay, the power order sent to the inverter. Now let's look at how this power order will influence the inverter entire system frequency. So what happens, or measure the frequency? What happens is that power command will influence the axis real current. There's this inverter level power control, and it just acts like the first order delay, just act like the low pass filter. Now the real current will really influence the PCC bus angle, and this influence is dependent on the grid strength. So grid is weaker, the influence is much more. So if you inject more real current, inject more power, the angle becomes or change more, something like this. And then the PLL phase lock will basically follow this angle. That's if we are using PLL to measure this angle, the PPY bus angle. So this measured angle then becomes the measured frequency if we take a d over dt. Okay, that is the entire frequency power current angle feedback system, which we ignore the voltage control influence. So for this one, we can get loop gain again, just like the up, then get the plant level control gain, delay, power order influence, and then XG divided by the grid strength, and then PLL, and then S. So this is very similar like the previous transfer function. It has 1, 2, 3, 4 components, except that now we have PLL. PLL is sort of like a low pass filter. And then, but we have S. S is like introduce 90 degree. Like introduce a 90 degree face forward, not face forward. So therefore, we can expect the shifting frequency will move forward, move a little bit further away in the frequency region. For example, here the same thing. I think it's if it's a 150 millisecond. Previously we see 2 hertz, or right now it is about 4 hertz shifting frequency. And we just pay attention to the blue line because the other one is the per day approximation. They are pretty accurate to capture the first phase shifting thing. Okay, so again, if you look at this entire thing, is that once we have phase shifting frequency, we wanted to gain, to keep below 0 dB to have gain margin. And this gain is influenced by this plant level control droop gain and grid influence. So therefore, again, weaker grid may cause issue, and the large FP gain may cause oscillation issue. And this is a set of parameters that we use that can cause issue. In this case, 0.3, that's the grid stress, that's the XG. So let's look at the, again, look at the a couple of sensitivity like influence of delay, because it's very similarly, if we have larger delay, then the frequency will push to the left. So here's a 3 hertz versus 4 hertz. It's 150 delay, then it's 4 hertz. 200 millisecond delay, that is like 3 hertz. But in this case, in fact, you can see the peak value is about somewhere at higher. So in fact, if push left, it's actually better. So we will not do this. But anyhow, we were just doing demonstration for the this simple cases, just do power order change. What will happen to the angle? So power to the angle, we're looking at feedback system. If you have power order, the 150 delay, that this is what you see, that it's about 4 hertz will come up. But 200 millisecond delay, then you will see 3 hertz and 7 hertz multimode oscillation, because it's 200 millisecond delay. It's like this. See, here's one, here's another one. Right? Yeah, here's another one. So it's very interesting to see there will be some kind of multi-mode, because covered here. So another is 7 hertz. All right, so that's again, so looking at there's the loop gain, there's the GFL, because there's a PLL. So PLLs matters. So slower sensor, for example, slower PLL is better. Why? Because you can see that we compare 2 PLL. One is 13 hertz, one is 5 hertz. PLL, that's the PLL's the GPLL, that it's closed loop, like PLL is the angle tracking another angle, tracking another PL angle tracking another angle. It's a low pass filter, but you can see that the 13 hertz has much faster responses. Now, once this GPL incorporated in the droop function in the loop gain, the entire frequency to power to frequency loop gain, then we can see, yeah. If we slower the PL response, we can completely completely push the loop gain down, and it's basically better for stability. And let's take a look in the right. For example, 13 hertz, you see oscillations, 3 hertz and 7 hertz. But once you switch to 5 hertz, it's marginally stable. The other one is marginally stable. The other one is like unstable. Right? So that's how you can just 2 sensitivity cases to show something. Look at that. Let's look at demonstration. So therefore, if we think about this one, that Here it's no longer voltage control issue because we have particularly tuned the voltage control to be slow. So voltage PI control is 0.1 plus ms compared to the previous one. So left side line tripping, but we don't include the FP control, droop control, but the right side we include the FP droop control, and FP droop control has the gain is 0.2. And you can see oscillation come up. So this oscillation, if you take a close look, it's more obvious, more severe in the P because if you look at Q, is not too much, but here is 0.6 scale. This is 0.4 scale, and angle is large change in the angle as well. And voltage, okay. So that's some comparison that we can see what happens. Yeah, so that's the possibility. This is the possibility. Suppose that you have FP control not designed very well. That there's a bigger gain. There's a gain that the system become weaker. This is a potential issue. Okay, so now we go to number 3. Number 3 is the over voltage issue. It's because of delay. Again, delay. So this time we put delay much larger. So we will see that the simulation results, starting from simulation. The simulation results we have is basically the grid voltage will have 30% dip from 3 seconds and the last 15 milliseconds. 15 milliseconds. So what will happen is that if the angle is increasing, that's good. The PL angle is increasing, but let's look at the action of the inverters. Inverter has this low voltage right through logic. So immediately if they sense the voltage dip, they will send more reactive power. That's the low voltage right through implemented in the inverter level. So then afterwards the fault cleared, then voltage recovered. On the other hand, let's take a look at the delay. The delay is that if we put 200 milliseconds delay in the for the best, then best order now will move up, right? Because they sense the voltage dividend now move up. So it's too slow, and then voltage will increase. In this case, voltage will increase after the fault cleared, and at 3.2, after like 200 milliseconds, the voltage will start to increase. But that's okay. But let's say the reactive power in the solar PV now start to have 300 delay now, 300 milliseconds. Now start to do that. That one start to increase again. It's the order, then it's follow the response. Now what will happen? Yeah, so the voltage again will increase. The solar PV, especially solar PV side, will increase. Now it achieves 120%. So then it may cause this over voltage tripping. So this is an example just showing that since the voltage dip, but the delay to push more reactive power, but already after the fault has been cleared, that can have the issue to cause this type of thing. So yeah, so it's just like a 0.2, then this will happen. Yeah, so one possible solution is that the delay cannot be that large, I think. Yeah, it's going to be better coordination. I think so. If you have like a 50 microsecond delay could be better, right? So you don't need to do this. Okay, so we have talked about all these delay influences. So now how do we model delay? In this case, the delay, usually the software package written, some software package written in the state space format, you have to convert to analytic format. So E2 minus TS cannot be modeled, cannot be simulated or analyzed. So one solution is this very popular one called the Patte approximation. So we can just use first order Patte like this and fifth order like this. So generally it's just like a transfer function to model this. So we'll take a look at what happens. So yeah, it's basically you have delays is just introduce phase lag. So this is the phase lag, and it's unity, so magnitude. And Patet approximation just give to you the unit gain, and then we just look at the phase lag. So phase lag, basically you have higher order, then it's more better approximation. A lower order and less accurate. So for 50 millisecond delay, then you can see that second order can be accurate up to 10 hertz, and 100 millisecond second order can be up to 8 hertz. And if you go to this sixth order, then it can be accurate up to 20 hertz. And here the sixth order can be good up to 40 hertz, right? Something like this. So it's all depends on the delay number. What is your exact delay? Then the order, then you can see, okay, well, the frequency region that you can capture. So we will show two examples. That one is the dominant frequency is 6 hertz mode, and it's 100 millisecond delay. So we will treat the blue line like you have to use the 20th order to create these simulation results. And because the 6 hertz mode 100 here, yeah, it's like 2-second order can actually be pretty accurate to capture up to 80 hertz. So you can see that second order, the green line can almost like say something like a stable, unstable can differentiate this one. On the other hand, if we have 20 hertz dominant mode, 20 hertz dominant mode, if we go to the next page, and it is a 50 millisecond delay. Yeah, 6 hertz, 4 hertz, 6 hertz then can capture that, but 2 seconds, second order cannot capture it. For example, second order cannot say this is the marginal stable, but if it's like 4 hertz and 6 hertz, you can really say something. Right. So that's the modeling issue. So the comment is regarding the voltage control and frequency control. So voltage control, you can have up to like, suppose we have 150 milliseconds, then it is like 3 hertz. Sometimes if for example this is 3 hertz delay, that is about 100 millisecond delay, that is 3 hertz. Yeah, so you can just use first order. You can just use second order to properly capture the shifting frequency. And then for this one, the frequency control, the dominant mode is about 4 hertz. So 4 hertz, then what we are using? Yeah, 4 hertz second order can capture that, but it can capture only one mode. But if you can capture like a 10 hertz, like this kind of mode, it's better. So therefore, fifth order, if you can see fifth order, the red line is much better to capture all the shifting frequency, two shifting frequencies. One is at 4, one is at 10 hertz. Okay, so finally, regarding all the challenges, now we will list the table that is just how you do testing and model recommendations, especially for the plant level delay. The recommendation that you should test for line tripping to check what will happen. You can also ramp up real power, tune the plant level gain a little bit, see if it's robust enough, increase delay a little bit, see if it's robust enough. And for the modeling framework, the frequency is in this level, like below 4 hertz, below 5 hertz. I think the positive sequence balance per day approximation should be okay. Or people, of course, go to EMG. Then there are other couple of challenges here that I have listed all the recommended, tested, and the modeling framework as well. So the appendix include the rest of these challenges that quickly documented on this appendix, but we don't have time to go through that. So if you have questions, please let me know. I will reply you. Okay, so thank you for your attention.